So in a previous video, we used an EEPROM as a decoder for a 7-segment display. So by hooking up a binary input here, so this is 6 or 4, 5, by inputting a different binary number on the address lines of the EEPROM would output 1s and 0s in the appropriate places to turn on or off the appropriate segments on the 7-segment display. But how could we build a decoder for 8 bits that outputs a number from 0 to 255 on 3 of these 7-segment displays? And that question came up in the comments on the video about using an EEPROM as a 7-segment decoder. The YouTube cuber asked, what do I do if I have multiple 7-segment displays displaying one decimal number? And there's some good replies in here. So Russell Teapot says, if I've got this correctly, you would need one EEPROM for each 7-segment display. And that's exactly what we've got here. We've got one EEPROM for each of the 7-segment displays. So we've got a 1s place EEPROM for the 1s digit, a 10s place for the 10s digit, and a 100s place for the 100s digit. And then the address lines, or at least the first 8 of the address lines for the chips, are all linked together. So if we put an address value on these 8 lines here, in this case, I'm putting the binary equivalent of 123, that same value is going to show up on each of these chips. So this chip is going to be at address 123, this chip is going to be at address 123, and this chip is going to be at address 123. And so at that address for the hundreds chip, it's programmed to display a 1. At that address for the tens chip, it's programmed to display a 2, and the ones chip is programmed to display a 3. And then they go on to say, let's say we want to represent the numbers from 0 to 15, we can use 2 EEPROMs. And this is exactly right here. So this shows for the address 0 through 9, that first EEPROM is just outputting all zeros, and the second one outputs the numbers from 0 to 9, and then it wraps around here, and that first EEPROM now outputs a 1 for 10 through 15. And then Jason Masters here kind of restates that and then says, yeah, if you link the address lines of the chips together, so all the chips get the same address, and you put the binary number on the address line, and the output of the chips will display the decimal equivalent. That's absolutely right. So simple. But then this is interesting. The YouTube cuber again says, yeah, another thing that I thought of is multiplexing through the EEPROM. So you get the binary number and the digit number as input. And then you get a binary coded decimal, or I guess you'd get the decoded 7-segment thing as your output. And it says you need a binary counter on the digit number input to start multiplexing. I like this idea. Rather than needing to have 3 of these EEPROMs, 1 for each digit, we can do it with a single EEPROM that drives all 3 digits. Now it's going to be a little bit more complex, but it's I don't think we're going to need to do anything that we haven't already done elsewhere in our computer build. So let's give it a try, and I'll explain more about how this multiplexing works as we build out the circuit. So this display module is going to be part of our computer. It's going to be the output for our computer. So I'm going to connect a new breadboard here right below the B register for our computer and build the display output here. And so we're going to use a single EEPROM. That's the idea of this multiplexing idea, the 28C16. And I'll start by connecting it to a single 7-segment display. And this is a common cathode instead of common anode, which were the ones we were using before. So I'm going to connect the common cathode here to ground through this 330 ohm resistor. And there is a reason I'm using a common cathode display here, which I'll go into later. And so I'm just going to connect the 8 output pins for the EEPROM to the 7 segments of the 7-segment display plus the decimal point. And I realize that's kind of hard to follow with everything on top of each other there, but basically what's going on is we've got these I/O pins, I/O 0, 1, 2, 3, 4, 5, 6, 7. Those are the pins that are connected here. And they're connected to the 7-segment display basically like this. So, this is what our 7-segment display is going to do, just 0 through 9, because we're just doing decimal at this point. And each of the segments, it has a letter designator, so A, B, C, D, E, F, and then G is the one in the middle. And then, of course, there's also the decimal point over here. And so this is the way that I've arranged the bit order. So the decimal point is the most significant bit, so that corresponds with I/O 7 here. And then it goes A, B, C, D, E, F, G, where G is the least significant bit corresponding with I/O 0 over here. So that's how I've hooked this up. But of course you can hook it up any way you want. You just got to make sure you know which bits need to be on for each of the numbers that you want to display. And now we can also hook up power and ground for the EEPROM so that it's powered. And then the control signals that we've got our chip enable, our output enable, and our write enable. Now chip enable, we want that to be active, so that's active low. Output enable we also want to be active, and that's also active low. And then write enable, we don't want that to be active. We don't want to be writing to this. And so that's active low, so we want to tie that high so that we're not going to accidentally write anything to this chip. And so that leaves just the address lines. So there's 8 address lines over on this side, and then address 8, 9, and 10 over on that side. And for now, I'm just going to temporarily tie those all low. And so that's the first 8 address lines are all tied low there. And then I'll also tie the remaining 3 address lines over here low as well. So with all of the address lines tied low, this chip is going to be addressing address location 0, and we'll see whichever bits are set on the output here. So let's add power, and we can see that we're getting all of the bits set. So all 7 segments plus the decimal point are on. So address location 0 on this chip is apparently programmed with all ones. And if we go to some other address, so address 1, 2, so it looks like this chip is probably erased if all it's giving us is all ones on the output. So let's pull the chip out and program it with something. So I've got the EEPROM in our Arduino programmer, and I'm going to come over to the code here, and because we're using a common cathode display now instead of a common anode, I'm going to make sure I've got the right programming for that. So this is the right bits that we want to have set for common cathode. So I'm going to go ahead and upload that and look at my serial monitor. And so it's programming. And okay, it looks like it's going to start by erasing the EEPROM, and then it programmed it, and it looks like it's got that program in there for the first 16 bytes. Okay, so let's pull it out and put it back in our other circuit. So we put this back in here now and connect power. So now we've got a 0, and if we go to address location 1, we've got a 1, and this is working as we would expect. But of course we want to have more than one digit. And so the way the multiplexing is going to work is we're actually going to drive all of the digits using the same data bits, and then we're going to switch on certain digits at certain times, which will hopefully make more sense in a minute here. So I'm going to add a couple more digits here, and what I'm going to do is I'm going to connect all of these essentially in parallel so that the outputs of the EEPROM go to all of them in the same way. So I've hooked all of the pins for the segments together. So if we connect the common cathodes for each of these to ground, we should see each of the digits light up the same way, assuming everything is connected properly, which things are getting pretty crowded down here. So let me see what's going on here. There we go. And so now if I change the input, all 3 of these digits should change. So there's 1, 3, 2, and so on. So of course this isn't what we want, but it does mean that we can control all of these digits from the one chip. And actually I've got a little extra room over here so I can add a 4th digit if I want, and I think there might be a way to use it. Because I think there will actually be a use for that 4th digit, which I'll get into later. But now what we need to do is build the multiplexing logic that cycles through each of these digits so we can display a different number on each digit. And to sequence that we need a clock, and I don't want to use the clock that is running the rest of the computer because we might want to run that at a different rate or whatever. So I'm going to build a separate clock just for the output display using a 555 timer. So let me connect a 555 timer over here. I'll connect ground and power. And then I'm going to connect a 2 microfarad capacitor from pin 2 to ground. I'm also going to connect pin 2 over to pin 6. Pin 5 I'm going to connect to ground with a 10 nanofarad capacitor. And I'm going to put a 100K resistor between pin 6 and 7, and then a 1K resistor between pin 7 and 5 volts, or between pin 7 and 8, I guess. Pin 8 is already connected to 5 volts. And so this is a simple astable configuration for the 555 timer. And if I hook the output, which is pin 3, up to an LED, which is going through a resistor to ground, I should be able to see this pulsing. So if I connect power, there we go. So we have a little clock running here. And so next what we want to do is we want to use this clock to sequence through each of our displays. And to do that, what we need is a small counter. So the 74LS76 has got 2 JK flip-flops on it, which is just enough to make a simple 2-bit counter. And we basically want to take advantage of the toggle functionality of the JK flip-flop to build a simple counter. So we want to basically just connect the preset clear J and K inputs all high, and then just use the clock, and every time the clock pulses, we'll get a toggle, and we can use that to build a counter. So this is the preset and clear for the first flip-flop, tying both of those high, as well as the J input and the K input. So those are all tied high. and then also the preset and clear for the second flip-flop, as well as the J and K inputs for the second flip-flop. And then of course this chip also needs power and ground to power the chip. So next we can connect the clock into our clock input for one of our flip-flops, and then we'll connect the output of that flip-flop into the clock input of the other flip-flop to create a counter. So we'll connect the output of our 555 timer to that clock for one of the JK flip-flops. Then I'll connect an LED to the output of that flip-flop, and also connect the output of that flip-flop around to the clock for the other flip-flop. And finally I'll look at the output of the second flip-flop. So now if we power this up, hopefully we'll have a working counter. And it looks like we do. So we've got this counter now. So it's counting from 0, 1, 2, 3, 0, 1, 2, 3. So that's counting from 0 to 3. And so we can use that count to control which of our digits we want to display. And to control that, I can use 2 of these additional address lines. So remember, we've got our 8 address lines down here that we're using to input which value we want to show. So right now we're inputting a 2, and we're seeing 2s. But we've also got these 3 additional address lines up here that we're not using. They're all tied to 0. Well, we can tie 2 of those to these counting LEDs over here. So instead of tying this address line to ground, I can tie it to this LED here. And instead of tying this to ground, I can tie it to this LED over here. And what you see is that when both of these are 0, we see the same thing we saw before. We see that 2. So once every 4 clock cycles, essentially, we get a 2 here. And then the other times we're getting just all 8s with the dot. So basically all of the bits are set. But what we could do is program this so that when the counter is at 0, it's outputting the number we want in the ones place. And when the counter is 1, it's outputting the number we want in the tens place. And when the counter is 2, it's outputting the number we want in the hundreds place. So let's go ahead and actually program the EEPROM to do that. So again, I'm going to put the EEPROM into our Arduino EEPROM programmer. And so just to summarize what we're trying to do here, we've got these 11 address bits, and we're using the bottom 8 of them, A0 through A7, to input the number that we're trying to display. So this could be anywhere from all 0s to all 1s, so 0 to 255. And then we're using address 8 and address 9 to tell us which digit we want to display. So if these are both 0s, then we want to display the ones place. And so if we put in, for example, if we put in the number 123 here, we'd want the output to display a 3. But if we set A8 high, if we put in 0 and a 1 for A9 and A8, then we want this to display the tens place for that same number. So again, if we've got 123, let's say here, then we want to display a 2. So that would be the tens place. And then if A9 is a 1 and A8 is a 0, then we'd want to display a hundreds place for whatever's in here. So again, if this is 123, we'd want to display a 1. So again, just as an example here, this is what we would actually want to see programmed in the EEPROM, for example. So at address 000 and then this 01111 this is the binary for 123 in decimal. And so because we've got the 00 here, the output is going to be the bits that we need to set in order to show a 3. But if our input is that same set of bits in the lower 8 bits, so this is still representing the number 123, but in this case, if we've got a 01 in these upper bits, then we want to output something different. We want to output the bits that we need in order to display the number 2 on the 7-segment display. And then same thing here for the hundreds place. If A9 is 1 and A8 is 0, and the rest of these are the same, this is still representing the number 123. Now we want to output whatever we need to output to display the number 1. In this case, it's just these 2 segments. And then, because we've got 4 digits, there is also this case that we have to handle where we've got a 1 and a 1 in A9 and A8. And in this case, we'll just output nothing. So all 0s will just mean none of the segments are on. So that 4th display will just be blank. So this is what we want to program. So we don't really want to just type out all of those, because that's going to be over 1,000 separate numbers, and we don't want to type all that out like this. So let's write some code that actually just fills in all of the numbers that we need to program into the EEPROM. Though I am going to use this part here, at least up to number 9. Yeah, so this part here, I'm actually going to copy that, and then we'll comment that out. And then down here, let's see, we don't need to erase the whole EEPROM. We're just going to be writing over a lot of this anyway. So I'm going to delete this code. And then here where we program the data bytes, rather than just programming whatever was in that data array. We'll call this digits. And so these are just the hex codes that we need in order to display each of the digits from 0 through 9. And so we want to start by programming all of the ones place. So we can go from address 0 to 255, and we'll do write EEPROM address, and then we want the digit that corresponds to the ones place for that address. So to get the ones place of the address, we can do address mod 10. And this % is the modulo operator, which essentially just divides address by 10 and gives you the remainder. So if address is 0, we divide by 10, the remainder is 0. If the address is 123, we divide that by 10, we get 12 with a remainder of 3. And so it'll, so this will give us 3, which is the ones place in 123. So this will give us whatever the value of the ones place is for address, but we don't want to write that. We want to write the digit for that. So what we can do is we can just use this as an index into digits. So if we say digits and then at that index, because this address mod 10 is always going to be a number between 0 and 9, because whenever you divide something by 10, the remainder is going to be between 0 and 9. So that's always going to be a number between 0 and 9, and so that's just going to give us whichever of these values corresponds with that position. So this should write all of the ones places to the EEPROM. Next we need to write all the tens places. So we'll go from 0 to 255. And actually address is probably not the best name for this. Let's call this value, because the value and the address are only the same for the ones place. So I'll just rename all of these value to be consistent. And so here we're going to write to value plus 256 is the address that we're going to write to. And that's because we're doing this case here where we're doing the tens place. And so A8 is always going to be set, and the place value of this bit is 256. So it's going to be whatever the value is plus 256, and that's where we want to program the tens, the appropriate code for the tens place. And so here we want to get the tens place. And so if we do address, or not address, value, oops, actually, this should be value mod 10. So if we do value divided by 10, because value is declared as an integer here, this divide by 10 will be an integer division. So it won't give us a decimal place, it'll just give us a truncated value. So if it's 123 and we divide by 10, it'll just give us 12. It won't give us 12.3. And so if we take that and then we do a mod 10, we'll get the 2 for the tens place. And so again, we can use that as an index into digits to get the appropriate code to display that digit. So we'll write that. And then we want to do the hundreds place, and it's going to be the same thing. So we'll just go through all 256 values, and in this case, the offset is 512, because we're writing now to this range here where A9 is set and A8 is not set, and the place value in binary of A9 is 512. So we just make sure we just add that to whatever our value is to put it in that address. So value plus 512, and then digits, we're going to index into digits for value divided by 100 to get the hundreds place, and then mod by 10, although that's probably not going to be necessary because we're only going from 0 to 255, so this should only be 0, 1, or 2, but we can do that anyway for consistency. And so this will write all the hundredth place. And then for that fourth digit, because we do have 4 digits, we just want that last one to be blank, so we can do a loop that just writes all zeros to that range. So this will be value plus 768, because both A9 and A8 are set. So you take the 256 plus the 512 and you get 768. And then for that whole range, we're just going to write all zeros because we don't want that digit to display anything. We'll just write all zeros. And we don't need this loop to write our data. So we'll do that, and then we can still print the output there. So let's upload that. And it's programming, and it's done. And, well, we just printed the first 255 bytes here, but you can see this should just be repeating that first 10 things over and over again, and it looks like it maybe is. But yeah, let's give this a try. Let's pull this out and put it into our circuit. So get the EEPROM back in the circuit, hook up power, and we see it cycling through 2, 0, and blank. But of course, it's not putting the numbers onto the individual displays. It's just showing them in sequence, which is not quite what we want. But we're getting there. And so if we give this another number, so let's say we give it that example like that 123, and you see 3, 2, 1, blank, 3, 2, 1, blank. And so what we want is we want the 3 here, the 2 here, the 1 here, and the blank there. So what we need is some way to sequence through these displays. And for that, what I'm going to do is I'm going to use our counter to then feed into a decoder. So to do that, I'm going to use the 74LS139, which is a 2 to 4 line decoder or demultiplexer. And so what it does is it's got 2 inputs, A1 and B1, and depending on what those values are, you get one of these data outputs goes low. And so basically you can imagine this A and B, we're going to use our counter here, which is counting from 0 through 4 in binary. We're going to use that A and B, and it's going to cycle like this from both being low to A being high, then B, then both. So that's what we've already got that. And then what happens is the outputs, it just cycles each of these going low in turn. So it just cycles through each of those. And then what we can use this to do is select which output digit we're displaying. And the way this chip works is pretty simple. It's got the 2 inputs, and it's essentially just using a series of AND gates and inverters to pick, based on how these inputs are set, which output to turn on. So if we put the 74LS139 up here, it's pretty simple to hook up. We just need to give it the power and ground, like we do with all of these. And then it has an enable pin here, pin 15 that's active low, so we want that to be active, so we'll tie pin 15 here to ground. And then the inputs are just pins 14 and 13. And I'm just using this top one because we're coming from over here, so just stay on that side of the board. So I'll just hook these two to those inputs. So now let's take a look at the outputs, which are on pins 9, 10, 11, and 12. And so you can see the outputs of this decoder, you've got all of the outputs on except for 1. And the one that goes off corresponds to our input as we're counting. This is very convenient, and this is also the reason that I used the common cathode displays, because what we can do is we can hook these outputs up to the cathodes here rather than just tying all the cathodes to ground. And that way, the only cathode that will actually be hooked to ground will be the one that we want to be displaying. For example, instead of connecting the ones place cathode directly to ground through this resistor, if I connect it to this first output here, you'll see the ones place is only on when we're displaying that 3, and the 3 is what should be in the ones place. So in other words, we're both displaying the correct digit and putting the correct address into the EEPROM to display that place value at the same time. And so I can do the same thing for the tens place. Instead of connecting that directly to ground through that resistor, I can connect it to the second thing here. And so now you see the tens place only shows up when we have a 2 there. And remember, the input here is 123. So we get the 2 in the tens place, we get the 3 in the ones place, just as we should. And then the hundreds place, same thing. Rather than connecting that directly to ground, we can connect it to this place here. And so now we only see the 1 when we're addressing the location in the EEPROM for the hundreds place. And then finally, this 4th digit, we can do the same thing. Although we shouldn't see much there because remember, we programmed all zeros into that last block of memory. And so now we've got the right digits in the right places, but this isn't quite what we want, right? Because we want our display to actually show us a number. We don't want to have to read it like this. This is kind of janky. But what we can do is adjust the speed of our clock. And so if I replace the 100K resistor with a 100K potentiometer, I can start to increase the speed by turning that potentiometer. And what you'll see is as it gets faster and faster, it looks more like 123, and if I go fast enough, you can't even tell that it's flashing like that. And so that's basically our display. Now instead of sticking this pot in here, I'm going to put the 100K resistor back. So now another way to slow this down is instead of using this 2 microfarad capacitor, I'm going to replace that with a 10 nanofarad capacitor instead. And that's going to give us a similar kind of effect. And with it running this speed, we don't really need any of these LEDs. They're not showing us anything interesting, so I'm going to pull all those out as well. I'm also going to clean up these wires here and just replace them with wires that are cut to length. And so there we go. We've got our 8 inputs here, and we can switch these to different values, and we get the decimal representation of whatever input is down here on our display. Now we've also got this last address line that we could do something interesting with. So right now, if we take that high, we just get all ones on everything because we haven't programmed the other half of this chip. So we could actually have two different types of display. We could program the first half of the chip the way we have for a decimal display, and then the second half of the chip could be programmed with some other kind of display. It could be hexadecimal if you want to do that. Or what I think would be interesting, and since we have this fourth digit, is you could program the second half of the chip to show negative numbers, or more specifically, you could have it decode 2's complement numbers, which could be positive or negative. So 2's complement uses an 8-bit number to represent numbers from between negative 128 up to positive 127. And so we could use this first digit to show the negative sign if we need to. So to display in 2's complement, we want to basically do the same thing, but instead of right now we're programming values or we're programming memory locations essentially from 0 through 1023, because this is going to be 255 plus 768 is 1023. So we're programming essentially the whole first half of the chip with our normal unsigned integers. And so for the signed integers that use the 2's complement, we're going to start at memory location 1024. So to program that, we're going to want to go value from negative 128. Oh, you know what? I just realized we might have a bug here because look at this. We're going from 0 to value less than 255, so we might not actually be programming 255. So let's actually give that a try. Let's go back here, set this to here, and let's try looking at position 255. I bet it's not programmed properly. So if we go to, let's see, that's 254, and if we change this to 1, yeah, look at that. We didn't program 255 because we said less than 255. So we need to do less than or equal to for all of these. So I'm glad I caught that. Now if we come back down to here, so our value is going to go from negative, for 2's complement, our value is going to go from negative 128 to positive 127. And again, our address is going to start at 1024. But we don't want to just add value to it, right? Because value starts at negative 128. So if we add that to 1024, we're actually going to be writing partway into this area before. So what we can do is we can take value and cast it to a byte. And what this will do is it will take value and treat it as an unsigned byte. So if value has negative 128 in it, then this will say, well, negative 128 is represented as a byte as 1 followed by 7 zeros, because that's how, because this is going to use 2's complement to represent that. So this should take value and using a 2's complement, convert it to an 8-bit byte, which should be a positive number, and then we'll use that as our address. And then what we want to write there is essentially the same thing as we have here, digits for value mod 10. But what I want to do is I want to take the absolute value of this. So if it's negative 123, then this will take the absolute value of that and give us 123 before we mod by 10 and look at the last digit. And so now we can move on to the tens place. So again, it's going to go from 128 to 120, or negative 128 to 127. And basically the same thing, but of course we're going to divide value by 10 first to get the tens place. And our base here, instead of being 1024, is going to be 1280, right? It's 1024 plus 256. And then for our hundreds place, we can just copy this again. And so this will be divide by 100 to get our hundreds place. And this will be 1280 plus 256, which is 1536. And so that'll be our hundreds place. And then we just need to do that fourth digit there, which before we just set to all zeros, but in this case, we could use that to represent our sign by setting a negative sign there. And so what we want to do is if our value is negative, so if value is less than 0, so if it's negative, then we want to write to our address, so it's take value and cast it to a byte to get a positive 2's complement representation of our value. And then here, our offset's going to be 1536 plus 256, which is 1792. And so if it's negative, we want to write, I believe, a 1, right? So 1 should be, this should be the one, that last bit should be segment G, which is the one in the middle that would look like a negative sign. And otherwise, if it's non-zero, we want to write to that location, plus 1792. In this case, we just want to write 0. We just want the display to be blank if it's positive. And I think that should do it. Yeah, and I'm going to add one other thing. I'm just going to add some print lines here so we can just keep track of what it's doing while it's programming, because it's programming the entire EEPROM. We're programming all 2048 memory locations in this EEPROM, so it's going to take a little while. So I'll add these print lines so that it's easier to see what's going on. Okay, so that should be it. So let's go ahead and upload this. Look at our serial monitor. And this is taking a little while. I'll speed this up for you. And it's done. So let's pop the EEPROM back in our circuit here. So we've got our 255 here. So that's fine. And so this should work just normally. So, you know, if we set some other values here, 127 or, you know, 123, 122, 123. So this is working normally. And these values obviously are lower than 128, but if we go up to, you know, 251, that's going to be positive, so because we've got this bit low. But if we want to look at our 2's complement, then we set this bit high. Now we're looking at 2's complement. So anything below 127 or 128 should be the same. So any of these other values should be the same. But if we set this high bit now to something, now we've got a negative number. So this is negative 13. So let's see, if we're in binary and we put in 11110011 in binary, we convert that to decimal, we get 243. And so that would be normally what it is. So if we go to our normal mode, so yeah, that's 243. If we go to 2's complement, yeah, negative 13. So that's right. So we are getting the right thing. And we can try some other things. I'm just going to move these around to just sort of some random things. So we've got negative 46 in there. I don't know, negative 62, let's say. So this is 11000010. And so if we go to decimal, yep, negative 62. And then if we're in unsigned mode, that should be 194. Yep, so it looks like this is programmed right and working. So now we've got an option where if we set this low, we have a normal sort of unsigned mode. So this will just represent numbers from 0 to 255. But if we set this high, then our output will show us numbers from negative 128 up to 127. And depending what we're using the computer for, we may want one of those output modes or the other, and we can set that using this input here. So I think that pretty much does it for our 8-bit display here. So we've got 8 bits coming in, and we're able to display it either as a signed 2's complement or unsigned. And we did it with only a single 28C16 EEPROM. So I think that's quite an improvement over the last time I built one of these where I used 3 of these, 1 for each digit. And we've got a 2's complement signed mode as well.